Hello everyone. So today we are going to discuss about a beginner's guide to advanced Kubernetes pod techniques. So Kubernetes has become the standard for container orchestration, and at its core lies the pod. It's the smallest deployable unit. While beginners often start with simple pod deployments, truly mastering pods requires understanding their advanced capabilities. So in this guide, we'll take you from fundamental concepts to advanced techniques, complete with the real-world examples and best practices. By the end, you will be equipped to design efficient multi-container pods, prevent common pod failures, optimize resource usage, and implement zero downtime deployments. So in section one, first we'll go through the pod fundamentals. So first, what is a Kubernetes pod? A pod represents a single instance of a running process in your cluster. Unlike Docker containers, which run in isolation, the shared networking, which is containers in a pod, share an IP address and port space. It also has a shared storage, so the volumes are accessible to all containers, and it also has a shared lifecycle, so the pods stop as a single unit. So in the key insight, pods are ephemeral. When they die, they are gone forever, which is why we use controllers like deployments. So this is a basic pod YML structure. So I'll create a directory here. So we are going to create a basic pod first here. So we'll create a file called deployment.yml. So we'll paste it here. So this is a basic pod. So here we got the API version as version 1. The kind is this is a pod. In the metadata, we gave the pod name as basic pod. So in the spec, in the containers, we gave the container name as main app, and we gave the image which is Nginx, and the container port number is 80. So this is a small and basic pod. So now we'll deploy it by using kubectl. So here the pod got created. To check, we'll use kubectl get pods command. So here you can see our pod is running here. So that's about a basic pod here. So in the section 2, we'll see about advanced pod concepts. So first is the pod lifecycle and states. So understanding pod states is crucial for debugging. So when the state is in pending, so it means it is waiting for the resources. So the common triggers are insufficient CPU or memory. So if the state is in running, it is successfully scheduled, and the common triggers are it's a normal operation. So when the state is succeeded, so the description is completed successfully, and the common triggers are bad jobs finished. So if the state is in failed, so at least one container got failed, so that's why it showed as a failed. So the common triggers are crash or error exit. So here if the state is in unknown, so the node communication got lost, so it is because of some network issues. So this is the debugging command. So we have to use the kubectl descript pod with the name of the pod to check to debug the pod. So here our pod name is basic pod. We have to give the kubectl descript pod command and the name of the pod here. So here we'll get total information of that pod. So along with the IPs, container ID, image ID, port numbers. So everything we can see about the pod here. So we can also check the logs by using this command here. So here our pod's container name is main app, and our pod name is basic pod. So click on enter. So these are the logs of our pod which we deployed just now. So that's how you can see the logs here. So the second one is init containers, the setup crew. Like init containers run before your main containers and are perfect for database migrations, config file downloads, and dependency checks. So in the real world example, you can use this code. So I'll give it as website.yml. So I'll save it and apply. So the pod got created. So these are the testing commands here. So to check status, we have to use this command. Like this is about kubectl pod, and we gave the name of the pod. So that status is running. So we can check init container logs also by using this command. So there is only one log which is config got created here. So here by using this command, you can verify whether the files are created or not. So here we have to give the name of the pod. So don't forget that. So here you can see the files got created. So that's how you can use these init containers here. So if you see how it works, so init container runs first, so creates config.json in a shared volume and uses a lightweight Alpine image. So no need for full app dependencies. Second one is main container starts. So Nginx access the config at etc nginx config.d and config.json. So the mtdir volume persists the file between containers. So why this matters means separation of concerns means setup versus runtime logic. Second one is resource efficiency. So only install setup tools in init container. And the third one is the reliability. So main app won't start until the setup completes. So that's how you can use the init container. So the key uses are generating config files, waiting for databases using until loops, downloading assets, and setting up permissions. So the third one is the multi-container pod patterns. So there are two patterns. One is the sidecar pattern, and the second one is the ambassador pattern here. So in the sidecar pattern, it adds helper functionality to your main container. So this is a full pod YML with sidecar pattern by using Nginx and Fluentd. So we create this pod and name it as nginx.yml and paste it here. And let's apply this. So the Nginx with the logs got created here. So can check the pod here. So the container is still creating. So let's wait for that. So here you can see the Nginx with logs pod, two pods are running here. So we can check the logs here of the web server. So these are the logs by using this command. And also we can check the logs by using the log shipper also. So these are all the logs here. And also, so let's see how it works. So in the container, the web server's role is main. So the action is serves web content and writes logs to varlog nginx. So the log shipper is a sidecar. It reads logs from varlog nginx and ships them. So the empty directory its role is a shared volume. So it allows both containers to access log files. So using sidecar container to handle Nginx logs. So in Kubernetes, a sidecar container runs alongside the main container in the same pod and shares resources like volumes. So in this example, we use an Nginx container, which is web server, which we saw just now. So to serve web traffic and write logs to varlog Nginx. So here we also used a Fluentd container, so which is a log shipper. So it acts as a log shipper. It reads the Nginx logs from the same path using a shared volume. So we use an empty directory volume called logs, so which allows both containers to read or write to the same directory. This design lets the main app focus on its job. So, sir, like serving web traffic. So while the sidecar handling process following the separation of consensus principle. So there is also another pattern which is called as ambassador pattern here. So it proxies the network traffic from main container. So we can use these YML code for that. So the warning is all containers in a pod share fate. So if one crashes, the entire pod restarts. So the next one is the resource management. So without limits, risky of noisy neighbor and OEM kills. So you can see the error like this. So if the resource got full, so this is the proper configuration for that. By using the limits here, uh, by using these limits, we can prevent the errors like this here. So the best practices are always set request equal to your app's minimum need. Set limit 20 to 30% higher than request and monitor with kubectl top pods by using this command. So here we are going to see the practical of this in the end of this session. So we are going to see about resource management, health checks, pod placement controls, pod distribution managers, sorry, budgets, and all these things. So is a code for that. So let's check. So before that, we'll see the theory of these things. So another one is health checks of probes. So if the probe type is liveliness, its purpose is app running or not. So the configuration tips are you have to restart unhealthy pods. So if the probe type is readiness, the purpose is app ready or not. So the configuration tip is it controls service traffic. If the probe type is startup, the purpose is app booted. So the configuration tip is protect slow starters. So this is the example configuration of that. So the critical settings are initiate delay seconds. So it avoids fall positive during startup. So the second one is period seconds. So it balance between responsiveness and overhead. So the third one is failure threshold. So it allow temporary glitches here. So we can use this command and we can initial delay to like we can give the timer here like it is 15 seconds here. So the period seconds is 5 and failure threshold is 3 seconds. So the next one is pod placement controls. So here we have both node affinity and pod anti-affinity. So here pod anti-affinity is for high availability. So here the use cases are it prevents single point failures and optimize for specialized hardware here. So the next one is pod disruption budgets, PDBS. So the scenario is ensure at least 2 or 3 payment service pods stay running during maintenance. So this is just an example. So the key concepts are it only affects voluntary disruptions, no, not the node failures. Here we can use the two strategies. One is minimum available, so keep exports running, and the second one is max unavailable, so it allow bypass to be done. So in the section 3, the production best practices are the pod design checklist like single responsibility principle. So one process per container, immutable tags, never use latest in production, proper labeling. So use app, tier, and environment labels. So next is security context. So run as non-prod when possible, and the resource limits prevent resource starvation. So here we can see the common pitfalls and solutions. If the issue is crash loop backoff, the solution is to check logs for errors by using this command. If the issue is of image pool backoff, solution is to verify image name or access by using this command. If the issue is pending pod, the solution is to check resource availability by using this command. So we'll take the hands-on of resource management, health checks, node affinity and pod anti-affinity, and pod disruption budgets here by using this complete command. So first we'll create this one. I'll give it as some app.yml and paste it here. So here we used the code affinity and anti affinity and resource management and also health checks and also the pod disruption budgets we'll see here. So I'll deploy this one. So it got created. So it is running now. So now we'll deploy the pod disruption budget also, which is PDB. I give it as pdb.yml. So I'll deploy this one also. Sorry, we can't see it here. So this pod is running here. So for the PDB, we have to use kubectl get PDB. So this is the PDB which we created just now, like 22 seconds ago. So you can also describe the PDB here by using this command. You can check all the things of the PDB here. So these are the things which we discussed now. So in the conclusion, exploring advanced Kubernetes pod techniques may seem challenging at first, but it's a crucial step toward managing real-world applications effectively. By understanding and applying these concepts, beginners can build more reliable, scalable, and efficient Kubernetes workloads. So this is about a beginner's guide to advanced Kubernetes pod techniques. So that's it for today. So yeah, thank you.